Imagine a powerful new AI model, one that doesn't just, process text, but truly understands images, videos, learning from them in a way that makes it incredibly smart and efficient too.
Right.
What if that wasn't just hypothetical? What if it's a brand new reality just released?
Well, that's pretty much what we're looking at today.
Exactly. Today, we're taking a deep dive into something really exciting, ERNIE 4.5. It's a new family of large-scale multimodal AI models from Baidu. Their technical report just dropped June 29th, 2025.
Fresh off the press, basically.
Yeah, and our mission today is really to unpack what makes ERNIE 4.5 so groundbreaking. We're going to explore its architecture, which is pretty unique, its training methods, how it's fine-tuned for the real world.
And the engineering behind it, too, making it run efficiently, even on less hardware than you might expect.
Definitely. Get ready to connect some serious dots. So let's start big picture. The ERNIE 4.5 family, this isn't just one model,
Yeah,
right?
not at all. It's actually 10 distinct models. They've got a mixture of experts, MOE models, and also a dense model in there.
And the scale is just wow. The biggest MOE has 424 billion total parameters.
Yep, 424 billion total. But importantly, only 47 billion are active at any one time. That's key for the MOE efficiency.
Right. And efficiency seems to be a major theme here. They're using their own paddle framework.
Yeah, and they're hitting 47% model FLOP's utilization, or MFU, in pre-training, which for models this massive, getting almost half your computational effort to be useful work, that's really, really good. Extremely efficient.
And that efficiency translates to performance. They're claiming state-of-the-art results.
Across the board, yeah. Text benchmarks, multimodal benchmarks, especially things like following instructions accurately, remembering world knowledge, understanding visuals, and that really tricky multimodal reasoning.
Okay, let's unpack that MOE concept a bit. We hear mixture of experts thrown around a lot. What is it, basically? And how does ERNIE 4.5's specific flavor, this novel heterogeneous modality structure, make it different?
Sure. So think of a standard MOE like having a team of specialized mini-brains, right? The experts. When data comes in, a router sends it to the best expert for the job.
Okay.
What ERNIE 4.5 does with this heterogeneous modality structure is, it's clever. It allows for both parameters that are shared across different data types, like text and images, and parameters that are completely dedicated just to one type.
Ah, so like generalists and specialists working together within the model.
Exactly. You got it. And this design really enhances how it understands multimodal inputs, images and text together without actually hurting, and sometimes even improving how it performs on just plain text tasks.
That's the surprising part. You'd think adding vision might dilute the textability somehow.
You might, but apparently not here. And one detail that helps is that their visual experts actually have only about 1/3 the parameters of the text experts. Makes visual processing much leaner, more efficient. They also use something called a modality-isolated routing strategy. Looking at their internal activation heat maps is kind of cool. You see the text experts lighting up in concentrated areas, while the visual experts are more spread out. It sort of visually confirms why having these separate experts makes sense.
So for you, the listener, what are the real advantages here? Unified modeling.
Yeah, unified modeling is one big plus. Everything's optimized together. Better data efficiency. Also, routing stability. It avoids this issue called router collapse that can happen when you try to just bolt on multimodal data to a text model.
Right.
And computationally, it's efficient too. Like we said, if you're only dealing with text, the model can just skip activating the visual experts altogether. Saves power, saves memory.
Okay, text and images are one thing, but video, that feels like a whole other level of complexity. How does ERNIE 4.5 actually integrate and understand video feeds?
That's a great question. They start with an adaptive resolution vision encoder. This is super important because it keeps the original aspect ratio of images or video frames. No distortion.
Right, because stretching or squashing would just mess up the visual information.
Totally. And for video specifically, they have an adaptive video sampling strategy. Basically, it intelligently picks frames to process based on duration and complexity, to fit within sequence limits efficiently.
Okay.
But the really novel part, I think, is their timestamp rendering technique. Instead of using extra text tokens to say, this happened at 5 seconds, they actually overlay the timestamp directly onto the video frames themselves.
Wait, like visually burn it into the frame the AI sees?
Yeah, like you might see the word Chongq appear on screen at the 5-second mark in one of their examples.
Yeah.
It gives the model these explicit time cues visually, which seems to really help with understanding when things happen.
That is fascinating. Building time right into the input. So how do they connect these visual bits, images, timestamp video frames with the text side?
They use a component they call an adapter.
Mm-hmm.
Its job is basically to align the representations from the visual side and the text side, bring them into a common space so the model can reason across them. And get this, it even treats a single static image as if it were a synthetic two-frame video, just for consistency in how it handles time across all visual inputs.
Huh. Clever. And positioning must be key too, right? Where things are in an image when they happen in a video.
Absolutely. They use what's called multimodal positional embedding based on 3D rotary position embedding. Think of it like giving every piece of information, whether it's text, part of an image, or a moment in video, a precise 3D coordinate, space, X, Y, and time. Handles that extra time dimension in videos perfectly.
Okay, so you need this sophisticated architecture, but none of it works without the fuel, right? The data. Where does all the training data come from?
Massive amounts, as you'd expect. They curate huge data sets, text and multimodal from all over. Web pages, academic papers, documents, images, videos. But it's not just quantity.
Quality control is key, I imagine.
Oh, massively. They have comprehensive data quality filtering pipelines, deduplication, getting rid of noise, even using other models to filter out low-quality stuff. You have to clean the data meticulously at this scale, or things go wrong fast.
And what if there just isn't enough high-quality data for certain specific things they want the model to learn?
Good point. They use data synthesis solutions for that. Things like self-distillation, where the model teaches a smaller version of itself, or multimodal conversion, creating image-text pairs from video, for example. And they combine this with a human model-in-the-loop approach. So humans are constantly providing feedback to refine the synthesized data, making it better and better iteratively.
That sounds labor-intensive, but probably necessary.
Absolutely. And they get quite specific. They categorize knowledge into 5 tiers and use key point-based data synthesis, especially for things like math, factual knowledge, and code areas crucial for reasoning. They tailor the data synthesis for the task.
So it's not just random data, it's targeted. What about image text stuff specifically?
They collect a lot of interleaved text-image data, think web pages or documents, with images mixed in. They even pull keyframes from videos and use automatic speech recognition, ASR on the audio, to get more text linked to visuals.
Okay.
And standard image-text pairs, sure. But they filter those using CLIP scores to ensure the text actually describes the image well, and even use AI to recaption images if the original caption is weak. Plus, they have this unique grid-style image understanding synthesis for things like complex charts or infographics.
Wow, that's thorough. Any specialized data?
Yeah, they also incorporate domain-specific data from industries like finance, healthcare, entertainment.
Right.
And getting audio transcriptions from videos and podcasts is another source they tap into for specialized language.
So managing all this data, especially during training across potentially thousands of GPUs, it feels like you need a system just for that. They mentioned something called REAO.
Yeah, REAO, record everything everywhere all at once. It sounds intense, but it's basically a very sophisticated data flow manager.
Okay, what does it do?
Its main job is to guarantee a bitwise deterministic token sequence. Meaning, every single time the model asks for data during training, it gets the exact same sequence of tokens in the exact same order, bit for bit, even if, say, a GPU node fails and the training job has to restart or shift resources around.
So it guarantees perfect reproducibility and consistency in the data stream no matter what happens in the cluster.
Exactly, which is absolutely critical for reliable large-scale training. Prevents weird inconsistencies or wasted computation from processing redundant data. It's a foundational piece for making the scale work.
Okay, so we've got the architecture, the intricate data pipeline managed by REAO. How do they actually teach the model? It can't be just one big training run, right?
No, definitely not. They use a very deliberate multi-stage training recipe for the vision language models, the VL ones. It's broken into 3 main stages.
Hey.
Stage 1, text-only training. First, they build a really solid language foundation. Train just the language part on text data, handling both standard context lengths like 8,000 tokens and long context up to 128,000 tokens. They adapt the positional encoding to handle that range. So get the language right first.
Makes sense. Build the base. Stage 2.
Stage 2, vision-only training. Now they start integrating the visual understanding, but carefully, so they don't mess up the language skills they just built.
Right.
This involves pre-training the vision encoder itself, then a phase called vision pre-alignment, where they actually freeze the main language model and just train the visual components in the adapter to connect them.
Ah, okay, so the language part isn't changing then.
Not in that phase.
Okay.
Then comes vision integration, where they jointly optimize the visual parts and the language model, but using only really high-quality image-text pairs. It's a gradual process of bringing vision in.
And the final stage?
Stage 3, joint multimodal training. Now they unfreeze everything. The whole model text vision adapter gets trained together on all the multimodal data, standard context, long context. Yeah. This is where it all comes together and learns to truly connect text and vision deeply.
That multi-stage approach sounds really crucial for stability. Training these huge MOE models, especially with mixed data types, must be prone to instability. Do they have specific tricks to keep things on track?
Oh yeah, several smart optimizations. One is called router orthogonalization loss.
Yeah.
Remember how the MOE router sends data to different experts?
Yeah.
Well, sometimes those experts can start becoming too similar. They homogenize, they lose their specialization. This loss function actively encourages the experts to stay different, to stay specialized. And apparently, it gave them a solid plus 1.44 improvement on text benchmarks.
It keeps the specialist specialized. Nice. What else?
Another one is token balance loss. When you're training with mixed image and text data, the number of text tokens in a batch can vary a lot. This can make the training signal, the gradient, really noisy and unstable. So this loss normalizes things by the total sequence length, not just the number of text tokens. It smooths out that variance, makes the training much more stable, especially when dealing with that mix of modalities.
That makes sense. Stabilizing the signal.
And they also use EMA, exponential moving average. It's a common technique, kind of acts like a smooth learning rate decay, helps stabilize training, and often improves the model's final generalization. They even implemented an asynchronous online EMA, so they can update the average model very frequently without slowing down the main training loop. Pretty efficient.
Okay, so that covers the core training. Now let's shift gears to fine-tuning, making these models ready for real-world tasks. They mention modular design.
Yeah, this is quite neat. ERNIE 4.5 is designed with a really clean separation between the text-only parts and the vision-related components.
And the benefit of that is?
Flexibility. You can deploy it just as a pure language model. They call that ERNIE 4.5 if you only need text capabilities.
Yeah.
Or you can deploy the full thing ERNIE 4.5 VL if you need the vision and language understanding. Lets you pick the right tool for the job easily.
Very practical. Now, for tuning the language model side, the LLM, they use supervised fine-tuning, SFT. And the data set sounds huge, 2.3 million samples.
Massive and incredibly diverse. They built a taxonomy covering 10 different domains: science, math, coding, logic, creative writing, safety, you name it. They even separate tasks that require reasoning from those that don't.
And they include multiple different good answers for the same prompt.
Yeah, multiple responses with distinct reasoning contents.
Yeah.
This helps the model learn that there isn't always just one right way to answer or reason, which makes it more robust and, well, creative, arguably.
Okay, but with such complex tasks, especially reasoning, how do you even judge if the model's output is good during fine-tuning? How do you create the reward signal?
That's a huge challenge. They developed a pretty sophisticated, unified rewarding system. It adapts based on the task type. For reasoning tasks, where correctness is key.
Like math or logic?
Exactly. They use things like rule-based verifiers, having another powerful LLM act as a judge, using a sandbox environment to actually run code and see if it works, and a reference-guided discriminative reward model. It's like a multi-pronged check for accuracy and logic.
Okay. And for non-reasoning tasks, like creative writing?
There, it's more about quality, coherence, safety. So they use checklist-aware verifiers as it meets certain criteria. Generative reward models that try to predict human preference scores, and other discriminative reward models.
Okay.
It's a really complex system tailored to different kinds of goodness.
Wow. Okay, so that's the reward. Then they use reinforcement learning, RL, specifically PPO.
Yes, proximal policy optimization.
Yeah.
And they do it progressively, which is interesting. Progressive reinforcement learning, PRO. They trade it in stages. First focus on logic, then add math and programming, and finally tune on general tasks. Builds up the capabilities systematically.
Sort of like the multi-stage pre-training, but for RL fine-tuning.
Kind of, yeah. And to make the RL even more stable and aligned with what users actually want, they use Unified Preference Optimization, UPO. This basically integrates ideas from Direct Preference Optimization, DPO, into the PPO loop.
How does that help?
It feeds the model pairwise comparative signals. This response is better than that one. This helps guide the learning more directly based on human preferences and makes the whole RL process more stable, less likely to reward hack, find loopholes to get a high score without actually being good.
Okay, that covers the LLM tuning. What about the vision language models, the VLMs? How do they boost their visual smarts after the main training?
Right, for VLMs, the focus is really on enhancing visual perception and reasoning capabilities together. They use a lot of synthesized data here, too.
Like what?
Things like programmatically generated visual puzzles, geometric figures, math function plots, stuff that really requires detailed perception. And they do this clever, fine-grained caption synthesis on real STEM images.
STEM, science, technology, engineering, math.
Exactly. They generate detailed captions for these images, but here's the key. They validate that the caption alone is enough information to answer related questions without seeing the image.
Whoa, okay, so the caption has to truly capture the essential visual information needed for reasoning.
Precisely. It forces the model to learn deeper visual understanding, not just surface-level descriptions.
So how does this all come together in the VLM fine-tuning process?
They use a framework they call thinking and non-thinking joint training.
Mm.
It's also progressive. Step 1 is fascinating. Text-only reasoning cold start.
Wait, text only for the vision model?
Yeah. They fine-tune the VLM only on text-based reasoning tasks initially. And amazingly, the model starts showing emergent multimodal reasoning behaviors.
Like what?
It might generate text like, let me take another look at the image, or refer to visual properties, even though it hasn't been explicitly trained on multimodal reasoning data yet in this phase. It suggests the underlying model is already making connections.
That is weirdly emergent. Okay, what's step 2?
Reject sampling for multimodal enhancement. Here, they start generating actual vision-related reasoning data across lots of domains, using rejection sampling to keep only the highest quality examples.
Building up that multimodal reasoning data set.
Right. And finally, step 3, thinking and non-thinking fusion. This combines the reasoning capabilities built up in the previous steps with more general, non-reasoning multimodal skills. They even merge experts from different fine-tuned models sometimes to get the best blend.
Very intricate. And they use RL for the VLMs, too.
Yep. Reinforcement learning with verifiable rewards, RLVR, tailored for multimodal tasks. For example, on visual STEM tasks, they turn multiple choice questions into open-ended ones, requiring the model to generate the reasoning steps.
Harder to guess the answer, then.
Much harder. For visual puzzles, they actually use 2 other LLMs as verifiers during RL. One checks the logical consistency of the steps the main model takes, and other checks if the final answer is correct. Double verification.
That's intense verification.
Yeah. And for practical stuff like UI2 code, generating HTML code from a picture of a user interface, they have a verifier that checks if the generated code actually looks like the target image visually. Really pushes for functional and aesthetic accuracy.
Okay, all of this training, fine-tuning, it relies on some serious infrastructure. You mentioned Paddle as the framework.
Yeah, the whole ERNIE 4.5 training stack is built on Baidu's Paddle deep learning framework. It's been optimized specifically for the challenges these large-scale multimodal MOE models present.
And handling the different components, the vision encoder, the MOE backbone requires special parallelism strategies.
Absolutely. They use a heterogeneous parallelism strategy. The vision transformer VIT encoder has different needs than the MOE backbone. So the VIT part might use standard data parallelism, while the MOE part uses a more complex hybrid parallelism involving data, tensor, pipeline, and expert parallelism, tailoring the strategy to the component.
Smart. And load balancing must be a nightmare with variable image sizes and video lengths.
Oh, definitely. They developed a hierarchical load balance strategy just for that. It balances the computational load and memory usage at both a coarse level, across nodes, and a fine-grained level within nodes, and they claim it gives up to a 32% overall performance improvement. That's huge in large-scale training.
32% just from better load balancing. Wow.
Yeah, it makes a massive difference when you're coordinating thousands of GPUs.
Mm-hmm.
They also focus on things like intranode expert parallelism to keep communication within a machine where possible, avoiding slower network hops, and clever memory-efficient pipeline scheduling to minimize how much activation memory they need to store.
Beyond parallelism, what other advanced tricks are they using under the hood?
They're using FP8 mixed precision training. Using 8-bit floating point numbers instead of 16-bit or 32-bit saves a ton of memory, speeds up computation, and reduces communication bandwidth. They've implemented fine-grained memory optimizations and operator fusion to make FP8 work well.
Does that impact accuracy? Lower precision can sometimes hurt.
It can, but they seem to have managed it well. They also use operator-level recomputation, sometimes called gradient checkpointing. Instead of storing all intermediate activations for backpropagation, you recompute some of them on the fly. It trades compute for memory, letting you fit bigger models.
And something called flash mask.
Yeah, that sounds like an optimization for attention mechanisms, maybe related to flash attention, but specifically for handling attention masks efficiently, especially important for those really long context lengths to save memory.
Okay, this scale, 10,000 GPUs mentioned. Things must break. Hardware fails. How do they handle failures without losing weeks of training?
Resilience is absolutely critical. They built a framework-native fault-tolerant system right into Paddle Paddle. It has several cool components. TraceHang, for instance, automatically figures out why a training job has hung by analyzing parallelism and communication records.
Finds the bottleneck or the failed part?
Exactly. And then there's the online SDC scanner. SDC is silent data corruption, where a GPU makes a mistake but doesn't crash. Really nasty to find.
How do they catch that without slowing things down?
Super cleverly. They use the idle time in the training pipeline, the pipeline bubble times, to perform redundant computations and verify results. So they can identify faulty nodes producing corrupted data without impacting the main training throughput.
Using idle cycles for error checking, that's smart.
Very. They also use parallelized warm-up after a restart to get performance back up to speed quickly. But the real star is probably ZCC.
ZCC.
Zero Cost Checkpoint. This is wild. It allows them to save a checkpoint of the entire massive model state at every single training step.
Every step. How is that even possible without grinding training to a halt? Checkpointing usually takes ages.
They figured out how to cleverly overlap the checkpoint saving operations with parts of the training computation that don't conflict. So the checkpointing happens in the background, essentially for free in terms of training time.
That is genuinely a game changer for large-scale training resilience.
Absolutely. The result, they say ZCC reduces the end-to-end automatic recovery time after a failure to less than 8 minutes. And it lets them maintain over 98% effective training time on that 10,000 GPU cluster. Almost no time wasted due to failures or checkpointing.
Incredible numbers. Okay, so they can train it efficiently and reliably. What about using it? Inference and deployment. How accessible is ERNIE 4.5?
This is another area where they focus heavily on efficiency. Even the largest model is designed to be deployable reasonably efficiently, partly thanks to that MOE structure.
Yeah.
But they go much further with quantization.
Making the model smaller and faster by using fewer bits for the number.
Exactly. They provide multiple options, FP8, INT8, INT4, and even 2-bit weight-only quantization.
2 bits? That's tiny.
It is. And it means you can run the largest ERNIE 4.5 model, the 424 billion parameter one, on, get this, 141 GB H20 GPU using the 2-bit version.
1 GPU. For a model that size, that dramatically lowers the barrier to entry.
Hugely. Makes state-of-the-art AI much more accessible. And they've worked hard to make this quantization good. They claim lossless W4A8 quantization, 4-bit weights, 8-bit activations using techniques like multi-expert parallel collaboration and outlier transfer to handle tricky values.
And the 2-bit, is it still accurate?
They call it nearly lossless, using a technique called convolutional code quantization, CCQ. It reduces the model size by a massive 80%. That's a huge win if the performance holds up.
They also quantize the attention cache.
Yeah, attention and KV cache quantization. This helps save memory during inference, allowing for larger batch sizes or much longer context lengths, which is often a bottleneck. They use static quantization and something called lightweight RHT to handle outliers there.
So smaller models, do they run faster too?
Oh yes, they highlight inference acceleration using optimized kernels. Their custom CKIN-LAS kernels for W4A8 reportedly get 70–80% of the theoretical memory bandwidth and give over 100% speed up on certain workloads compared to standard implementations.
Faster than things like flash attention.
Their efficient attention kernels are benchmarked as 1.68 times faster than flash attention 2 and 1.48 times faster than flash attention 3. So significant speedups there.
Wow.
Plus, they use speculative decoding with a multi-token prediction module, which can boost the output tokens per second by around 60%.
And for deploying the absolute biggest model?
They have a setup called PD, pre-fill decode, disaggregation deployment. It separates the initial processing of the prompt pre-fill from the token generation decode onto different resources, achieving really high throughputs like 56K input tokens per second and 18K output tokens per second per H800 node. With sophisticated load balancing, too.
And it runs on more than just NVIDIA.
That's right. They emphasize multi-hardware compatibility listing support for Baidu's own Conluxin XPU, plus Hygon DCU and Ascend NPU, broadens the potential deployment scenario significantly.
And finally, they're open sourcing parts of this.
Yeah, which is great for the community. They're releasing ERNIE Kit, a toolkit for industrial-grade training and compression. It includes things like low-bit quantization-aware training, QAT, letting people fine-tune efficiently, maybe on just 16 GPUs.
And for running the models.
They're open-sourcing Fast Deploy, their inference and deployment library. It's compatible with popular tools like VLLM, has comprehensive support for all these low-bit quantization formats, and handles the multi-hardware deployment, really trying to make the whole ecosystem accessible.
Okay, let's try and wrap this up. So what does ERNIE 4.5 really represent?
Well, it's clearly not just another LLM. It's this meticulously engineered family of models pushing the state-of-the-art in multimodal AI, text, image, video understanding. It delivers top performance, sure, but crucially with remarkable efficiency in both training and deployment.
Right. And you, the listener, hopefully now have a much clearer picture of the innovations driving that unique heterogeneous MOE architecture, the careful multi-stage training, the advanced optimizations, the robust fault tolerance. It's a lot of engineering.
Absolutely.
Yeah.
And the fact that they're open sourcing key parts like ERNIE Kit and Fast Deploy means these powerful capabilities aren't locked away. They're becoming tools for broader research and development. The ability to unify understanding across text, image, and video so effectively is a major step.
So as ERNIE 4.5 makes its way out into the world with this deep grasp of both language and complex visual information, it really makes you wonder, doesn't it? How might this next generation of truly multimodal AI fundamentally change how we interact with digital content, how we learn from it, maybe even how we create it in the, very near future?
That's the big question, isn't it? We're just starting to see what's possible.